the next talk. In the next lecture, Amin Fahang is going to talk about new tracer in ISM, unknown DIBs. Amin, are you ready? Amin, do you hear me? Can you hear me now? Okay. I can hear Amin Fahang, Dr. Fahang. May I ask technical people to check the connectivity of Dr. Fahang or not? Amin, do you hear me? I think we have a problem with connectivity, yes? We can hear you.
Can you hear me? Great, thank you.
Yes.
Okay, finally we got it. If Mohammed confirmed that anybody can hear me.
Yes, please.
Okay.
Do you hear me now?
Yes, I hear you perfectly. Okay.
Let's start this talk.
Thank you so much. Thank you so much for giving this opportunity to me for having talk at Zanjan University. Unfortunately, I cannot be in Zanjan, a beautiful city. But before starting my presentation, I would like to appreciate the organizers of this meeting, especially thanks to Hossein for all his efforts for doing everything online. I know based on the infrastructure that we have, it's a little bit complicated, but thanks to Hossein and his crew. In this presentation, I'm trying to talk about some unknown molecule. I call them DIBs. They are diffuse interstellar bands. Maybe you haven't heard of them. Maybe you're forgiven. But DIBs are a bunch of unknown molecules that can be seen pretty much every line of sight that crosses the interstellar material. They have been called an embarrassment of the modern science, which is why we not prefer to talk about them. But in this presentation, I try to explain what we did for better understanding this unknown molecule. How can I leave my video, just show my presentation? Okay, I could continue. Okay. Let's ask a question. Suppose that you are observing a very resonant direction in the ISM, and then all atomic and molecular layers would be removed from your spectrum. What is the remaining residuals? The answer is the white spectrum here. The white features, these white features are more than 500 unknown molecules that are presented everywhere in the ISM, and also they are located in the visible range of the spectrum. They are also in the near UV and near IR. I will talk about them, but most of them are here in the visible range of the spectrum. We call them diffuse interstellar bands. Why diffuse? Because they are wider than typical atomic or simple molecule. Just look at this strong feature. This is for the 430 angstrom deep, which it's 30 angstrom. 30 angstrom. The typical width of the narrower lines in this diffuse interstellar bands are half angstrom, which is still wider than any atomic, not actually any, but most of atomic lines, and therefore this wide width make the wings of the spectrum wider, and this is the reason that we call them diffuse. I explain why we call them bands in the next slides, but just accept this from me. Right now, I will reach that. The first dip actually have been observed by Marie-Lee Heger in 1919, about 101 years ago. At that time, just 2 dips have been observed with unknown carrier toward a very famous direction in the ISM. But at that time, Marie-Lee Heger thought that these features actually are coming from the stellar atmosphere. Just after 13 years, another research showed that no, those features actually was coming from the ISM, not from a stellar atmosphere, and that was the beginning of a big challenge in modern spectroscopy, the big mystery in modern spectroscopy. And right now, in 2020, that I'm talking to you, more than 500 unknown deep carriers have been detected in the ISM, and we don't know many things about them. We could actually ask this question after. Okay.
Sorry, could you please turn off the webcam? We have a problem with the connectivity.
Just stop sharing webcam, right?
Yes, thank you.
Is it right?
Yeah, that's fine.
Great.
I'm sorry.
And after 100 years, we just know some few facts about them. Not many things. For example, we know there are hundreds of interstellar absorption features from near UV to near IR. Near UV is placed in this region. I will talk about that in the last slide. And we know that some of them are very strong, like this feature, but most of them are rather weak. We know that some of them are broad, but most of them are very narrow. And we know that deep carrier are pretty much stable during time, and also they are widespread. I mean, from widespread, they are observed everywhere. Every direction that we observe, we could see these diffuse interstellar bands. For example, we could see them in our Milky Way. These 2 features that you see here are 2 famous deeps, 5780 and 5797 deeps, that you can see that they have been observed in the Milky Way, and also they have been observed in M33 galaxy. They have been observed in Antenna galaxy, for example. Look at these features. They have been observed in Magellanic Clouds. They have been observed in local universe. Already we did some observation of these DIBs, presentation of these DIBs in very hot local bubble near our sun, that show that these molecules actually could live in harsh environment, in neutral environment, in cold environment. I know in every environment that we know in the ISM they could be reside, because they are very different. They could be everywhere. We observe them in very hot. The temperature of this region is 1 million Kelvin, but what we observe some DIBs in that, and also we believe that if we suppose that they made of carbon, I will explain why we think they made of carbon. But let's suppose that they made of carbon. If they made of carbon, about 0.5% of all cosmic carbon could locked up in this molecules. Just look at the strength of this line. The strength of this line, the width of this line is 30 angstrom, which is made of carbon. Is definitely could show that about 0.5% of all cosmic carbon could locked up in this molecule. Therefore, they are very important in seeking for life in every single study of chemistry, evolution of galaxies. They are important. But we don't know anything about them. But why we call them? They are molecules actually. Look at the profile of these DIBs. This is one of the famous DIBs that we know, 6614 DIB, and you can see 3 different substructure in that. Actually, not 3 different. 1, 2, 3, maybe 4 and 5 substructure. 2 broad features are in the red part of this profile. The only molecule could produce profiles with substructure, because maybe the transition are coming from the vibration of molecule, the movement of the molecule, other process that the molecule just related to the molecule. Therefore, we believe that these features are molecular. And also, the width of this profile is so broad and wider than any typical atomic line in the ISM. So they are molecule. But what is the behavior in the ISM? I bring 2 examples, two famous examples here. The upper spectrum, the upper spectrum that you see here is the zeta OPH direction, which is a shielded region. What mean I'm saying shielded? Shielded means that the dense dust and gas prevent penetrating any high energy photon in this region. So we expect that everything in this region be neutral. But the lower spectrum is the Sigma-Skousen direction, which is a region with UV radiation photons, very high UV radiation photons, and therefore high energy photons are presented in the region. And then compare the strength of 5780 DIBs to each other. In 2 different regions, the strength of 5797 DIBs are quite similar, but the strength of 5780 DIB reduces when located in the shielded region, and is very stronger in the UV radiated region. Therefore, although we don't know their carrier, but we could show that they are a family of molecules that react differently in different environments. Sorry. And they are not same molecules. So these 500 unknown molecule could not be same molecule. Maybe 2 or 3 of them by chance be transition of same molecule, but not all of them. They are unique molecule, but they could be belong to a family of molecules. But again, let's look at these spectrums. These 2 directions are 2 completely different environments in the ISM, but we see same features, for DIBs and different features for other DIBs. So why we don't use DIBs as a diagnostic tool for extracting the ISM properties? That's a cool thing, right? And let's come back to the question of what could be the candidate for carrier of these DIBs. There are many debates for the candidate, but 3 main candidates are listed here. The first candidate are carbon chains. Carbon chains are simple carbon molecules that connected to each other and produce a chain. The second one are PAHs. PAHs are polycyclic aromatic hydrocarbons that are organic compound containing some carbon and hydrogen that compose of multiple aromatic benzene rings. You can see here the benzene rings and reproduce in different shapes, but they are flat, maybe some till at the edges, but they are flat. The last one are fullerenes. Fullerenes are just made of carbon, but in 3D shape, like ball. Look at the C60 fullerene. C60 is a ball made of 60 carbon that is not presented on Earth. It's just in the space. And C70, we have lots of fullerene, but just one of the fullerenes have been observed in the ISM. In 2010, the first fullerene, C60 and C70, the red spectrum and the blue spectrum, you can see their features in the IR region, have been detected by Kami, Jan Kami. And that was the first detection of fullerenes in the ISM. After 5 years from this detection, Campbell in 2015, for the first time, find that the two strong deep on the near IR region actually are C60 plus transitions. So after 100 years, about 100 years, among just 500 unknown molecules, just 2 of them have been confirmed that are belonging to C60 plus. And still many debates are ongoing for this C60 plus and C60 and C70, but the community right now accept that these 2 features, these 2 narrow features, are belonging to C60 plus, and that's a big step in understanding the ISM chemistry and ISM properties. But let's ask the main question in this field. The first question actually is, what are deep carriers? I show you that we don't know their carrier. Just 2 of them have been detected after 100 years, and maybe 100 years later we just find 2 of them more. How are these species formed, excited, and destroyed? We don't know anything about them because we don't know their structure, the chemical structure. And also, the last question, which I think is the most important one, is that what can these features tell us about the physical condition of the environment? I show you that their properties in different environments are completely different. Therefore, they could tell us many things about the chemical and physical conditions of any interstellar cloud, any galaxy evolution, and they are very important. They could be very important. But what is the weakness of this study? Well, actually, for getting forward for better understanding of these molecules, we have to done some very good sensitive observations with large number of DIBs in great details to establish actually the quantitative relationship between the DIBs and properties of other line of sight. This is very important. For doing this, in 2014, we did a very large survey using VLT telescope. Sorry, just a second. Yes, we did a very large telescope. I mean, by very large, the very large proposal are kind of proposal that take huge time of telescopes, and they are rare, but we fortunately we did one of them. We observed 300 hours using UVS instrument on the VLT telescope. We observed 124 different targets, mostly O and B stars, with wide range of interstellar parameters like different dust properties, different gas properties, different temperatures, and we try to observe from near UV to near IR to allow us to include many known atomic and molecular lines. and also to the sensitivity of this this observation is very high. The signal to noise is 1000 in the red arm, but in the blue arm, its signal to noise reached to 700, which is a great signal to noise. It's not enough for some kind of study, but it's enough for sensitive study of diffuse interstellar bands. And also the resolving power of this instrument is very high. In the blue arm, the resolving power is 72. I forget about this 72,000, and in the red part is more than 1,010, which is great. And this is one of our results. As I told you, the C60 plus was confirmed that is responsible for 2 DIBs, but for the first time, using EDBLES survey data, we find substructures in C60 plus. This region is not mapped because of the telluric contamination, and you can see that there are some substructure. This substructure actually could change with temperature in any ISM, therefore are a good indication for determining temperature and other physical condition of the ISM. In one of the study that I show you that the DIBs are presented in the visible range of the spectrum, but there was not a systematic study of near UV region from the ground-based telescope. Observing near UV region is very complicated because increasing the signal to noise is very hard, and also the ozone contamination make everything worse. And this is the reason that the people don't like to work in near UV from Earth. But we did that using UVS telescope, UVS EDBLES survey. Yeah, I bring all detected atomic and molecular lines in the near UV. You see here, we find for the first time 12 OH plus molecules in the near UV. We find OH, we find NH, CH, CH plus, CN molecules, and also iron, sodium, and other lines. And also, let me, this paper is going to be published, but let me say you that we find about 15 new DIBs in the near UV that already have not been detected. Using the EDBLES, we find 15 new DIBs. And also, we could use DIBs as a diagnostic tool. In this study, we compare the archival data from UVS with the EDBLES data. The blue spectrum is the EDBLES data, and the red one is the archival data. You see that we see 4 different DIBs in the archival data, which are completely disappear in this EDBLES data. This show that we detect very small scale structure in the ISM using DIBs. In 2005, that archival data was observed a very small structure, but after 10 years, because the background star is moving, actually our line of sight didn't pass through that small scale structure. We estimate the size of this structure to 60 AU. It's something similar to our solar system. So using DIBs, we could find very small scale structure. I think this is one of the smallest scale structure that have been detected in the ISM. And but another question is arise: why only these 4 DIBs are showing up in that small scale structure? Why other strong DIBs are not presented in that that structure? Does the carrier of these DIBs are different from others? Does they are belong to a family of DIBs or not? We could answer this question with further observation of these DIBs, but I bring the all people that are working on this EDBLES survey. The PI of this work are Jan Kami and Nick Cox. Also, we are working in this group. And yes, thank you so much.
Okay, thank you so much for the nice talk. We have time for a couple of questions. Please ask question. Mahmoud, do you have a question? Please.
No, Mohammed, I don't have any question.
Okay. Please ask your question. You can turn on your microphone and ask your question if you wish. Somaya, please ask your question.
Hello. Thanks, Amin, for your nice talk. I have a question. I'm interested in knowing how many diffusive bands already have been detected in ISM, and I mean, how do we know that our detection are, I mean, can be proved during the, I mean, some experiments in the lab?
Well, thank you. Thanks for the question. I said in my presentation that more than 500 DIBs have been detected in the ISM, but frankly, trying to produce them in the lab is very hard, because suppose that they have been formed from benzene, and they are large molecules, means that they form from 20 to 200 carbon atoms. And if we just suppose that they made from 100 atoms based on 6 carbon in the benzene rings, we could make 10 to power 18 different state of molecules, that is, which is completely impossible to make them in the ISM. The only way to try to produce them in the laboratory is to minimize and increase the properties of these DIBs, and then by knowing the properties, try to select some specific kind of this molecule and try to produce them in the lab. But every laboratory experiment was failed for finding this species.
Okay, thank you.
Thank you very much.
By Sohrab Rahwar. He asked, can you detect complex amino acids molecules?
Well, yes, already some amino acids have been detected in the ISM. I don't remember the name right now, but yes, I can say that some of them have been observed in the ISM, and also some glasses, silicon glasses, have been observed in the ISM, especially in the IR region. But unfortunately, I don't remember the name.
Okay, thank you. There is also another question. Where does DIB exist? In the coldest molecular cloud that is about to from a star, or in any gas cloud?
DIBs actually exist everywhere. We observe them in neutral environments. We observe them in ionized environments. We observe them in cold environments. And in 2019, we published a paper that we confirmed that they exist in the local bubble. If you don't know, the local bubble have a temperature of 1 million Kelvin. They actually exist in that high temperature. There are some reasons that why they could exist in high temperatures, but yes, they exist in every environment. If I answer your question correctly.
Okay. There is another question. There is another question by Hamid Hassani. He asked about the capability of MUS EULT data in order to seek for white DIBs.
The problem of MUSE is its signal to noise, actually. Just a little number of these DIBs are wide, and therefore could be definitely could be observed with MUSE. But for more reliable study of these molecules, we have to go for high resolving power, low high signal to noise observations, and therefore I don't think the MUSE is a good one for systematically study the diffuse interstellar band. Otherwise, MUSE could be used for study the broad features in the in the spectrum, because its spectrum is continuous, and therefore we don't have the problem of order merging in the UVs that we had already, and we could use them for broad feature. But for narrow feature, it is not possible. I believe that it's not possible for use MUs. That's why we use UVs instrument instead of MUs.
Okay, thank you. I don't know. Okay. Okay, thank you for the nice talk. We can start the